And starting the live stream. Well, happy Wednesday night to everyone. This is a ham radio beginning class and also a TV program. We produce it for YouTube, so it has elements of all sorts of different things going on here. And this is where we have fun. Soon to have some radio fun. Certainly when you get your ham radio license, getting on the air is just gangs of fun. But we will be incorporating some of that fun little later on in the class. What we're doing right now, tonight we're going to go over Chapter 3 in this book. We use the American Radio Relay League License Manual for the Technician class. This is the 5th edition, and we go chapter by chapter each week. And as we get started in the book, there's a lot of information in the first chapters that makes it kind of a slog for some folks who have never been exposed to electronics or some of the concepts we have here. And I've gotten some feedback from students that say, "Hey, Gary, I'm confused." And I tell them, this is perfectly normal at this point in time in the class. Just keep going. You will get it. Oh yeah, did I say? My name is Gary, ham radio call sign Whiskey for Echo Echo Yankee. And we've got a Zoom classroom of about 14 students right now, with about the equal number watching us on YouTube. So great to have you with us tonight. So tonight we're going to talk about Chapter 3, Electricity, Components, and Circuits. There are 3 sections in the book, in this chapter, Section 3.1 is the biggest. So what we're going to be doing is we'll go through section 3.1 and then all of the questions. Then we'll take our 5-minute intermission and we'll come back and complete the last 2 sections. So this is an amateur radio licensing class. You could say that it's a very basic introduction to electronics. And some students have asked me, well, Gary, why do I have to know all this stuff? Come back to me just for a second, Bruce, if you would. So we mentioned last week that the FCC wants us to have some understanding of electronics, just because we have the capability and authority to build our own ham radio equipment if we so desired. The other thing, and I'm going to talk about this in the very last chapter in the book, which is the safety chapter, is that I contend that ham radio is an adventure. Yeah. Sitting behind at a desk with my radio, tuning in signals, that's an adventure? Well, an adventure has a lot of different component parts. You'd say mountain climbing, certainly that's an adventure. But they don't start on the mountain. A mountain climber has a lot of preparation and work that they have to do. They have to obviously work on themselves, exercise, be strong. They have to do research on equipment, make sure that they get the right stuff. They have to work on techniques and learn how to self-rescue and all of that. That's the stage we're in right now. We're in the preparedness stage of this adventure. We're working on getting things ready for us to begin our ham radio fun, which is up and coming. So hang in there. We're going to get there, and we're going to try to incorporate, for the very first time, some of the ham radio adventure right here in the classroom, and some of our later sections when we have some extra free time, we'll be able to do that. So tonight, let's start with section 3.1, and we're going to go back to the very basics of electricity, and that's an insulator and a conductor. So you can go ahead and in the Zoom classroom and unmute. Can you name me what some good insulators to the flow of electricity or flow of electrons might be? What do you think?
Glass.
Glass, that's a great line. Yeah, okay. Anything else?
Rubber.
Rubber, plastics, ceramics. So yeah, you get the idea. Those are insulators to the flow of electrons. Now, how about conductors? Good conductors?
Copper.
Copper, very popular. Gold, silver, yeah, so we've got the idea. So insulators and insulating materials. So the materials of the glass and the rubber and the plastic, you can actually, they'll make insulators that are designed to inhibit the flow of electricity, even arcing. And so the insulators you see here are made just for that. These you might find on the end of an amateur radio antenna. And there's a reason, because the end of most amateur radio antennas hanging in free space is a high voltage point. You'll learn more about that coming up. So the insulators here are made for that purpose. Conductors, wires. Oh, we got wires. This is supposed to be a wireless hobby, but you're going to discover that there are wires everywhere in your ham shack, and so we need to keep that in mind. Conductors and insulators, and what they're conducting is the movement of electrons, which could be called an electrical charge, sometimes also called a current. And metals are good for this, the copper and the gold and the silver, because they have many free electrons in their outer atomic shell, the outer valence ring. And these free electrons allow the movement of electrons or current through a wire, through a conductor. Whereas rubber or glass, no, they don't have those free electrons. So that's the underlying basis. And the electric current, we can put together a circuit. Here's a very simple circuit, a schematic diagram. And so this is the schematic symbol for a battery. You can see the plus terminal of the battery is indicated here. And you'll see that electrons flow from the negative side of the battery. When the switch is closed, current flows through the lamp, lights the lamp. But when the switch opens, current is interrupted. So this is a very basic, simple circuit with a battery that is providing voltage or pressure to move electrons, which is the current in the circuit, going through the lamp, which is the load, which has a resistance of some sort to that current flow, and then a switch, which is opening and closing to enable or disable the circuit. And if you read in the chapter beforehand, you would have noticed that we have these key concepts. Voltage is like pressure. You can, the analogy to water pressure. If you pump water up high into a water tank, and you have pipes connected down from it, if you open the valve on a pipe, water will flow out because of the pressure of gravity on the water forces the water down. So voltage is like that. Voltage is the pressure that is pushing the current through a conductor. The current is the water. The current is the flow. Oh, and by the way, a lot of science uses French terms for whatever reason for some of their symbols. So that's why the symbol E is used in many formulas for voltage. Yeah, we don't use V, but it goes back to the French. You'll see here in another slide. Current, the symbol I is used, even though the measurement of current is done in amps or amperes. Resistance, that's that lamp in the circuit, it's resisting current flow, it's opposition to current flow, and resistance is measured in a unit called ohms. We'll talk more about that coming up. And then power. Power is the energy that is being used by the load or a device or whatever. Power is the rate that an energy is being used. The symbol is W, and the power unit is in watts. And what we saw was a circuit, any path through which current can flow. And my friend Dave Ivey, KE4EA, found this pictorial online, which you might find useful. There's Mr. Volt trying to push Mr. Amp, or the current, through a conductor, and there's the resistance, Mr. Ohm, trying to inhibit it. So that's what's going on even in the simplest or the most complex electronic circuit. Some function of this is going on. So as a review, E, the symbol for voltage, is electromotive force. I is the intensity of current. R is the resistance, using the Greek letter omega for ohms. So voltage, E, measured in volts. Current, I, measured in amps or amperes. And resistance, R, measured in ohms. And here's the descriptor, the pressure, the rate of electron flow, or a flow inhibitor. Those are the various things that describe it. And so volts, amps, and ohms. Come back to me for a second, just Bruce. So you will hear me throughout the course. When I pronounce, I very carefully try to pronounce ampere. But I had an electronics instructor, Mr. Zielinski, back in the day, who always used to pronounce it ampere, like pH, ampere. And you're going to hear me do it. So I just forewarn you, it's ampere. That's the proper pronunciation, but you're going to hear me do it. Thanks, Mr. Zielinski, appreciate it. He was a great instructor, by the way. So DC current is what we would find from a battery. And you just saw it there. And what we mean by direct current, or DC, is that, so here we have a graph of amplitude or voltage amplitude and time. So that's what we're looking at here. And here's 0 volts. Here is plus some voltage. And you see that for a DC voltage, it stays at that voltage level constantly all the time. That's what DC voltage is all about. And so what you get out of a battery, for example, is direct current, or DC voltage. What you get out of your wall outlet, on the other hand, is not DC. It is what we call alternating current, where, again, here's the 0 volts line. And in this case, the voltage where we've decided to look at it starts going negative, then comes back up to the 0 line, then it goes positive. It's alternating between negative and positive, 0, negative again, and up and down and up and down. In the United States, we use 60 cycles per second, or 60 hertz coming out of the wall. That's an alternating current that's happening 60 times in every second. So the thing about AC will go plus, and AC will go minus. DC, on the other hand, always goes either plus or minus, depending on the polarity, and then stays there. It never goes the other way, never goes negative in this case. So if it never goes the other way, then it's DC. If it goes positive and then negative, then positive, then negative, that is AC. And we're looking again at amplitude over time. So with that in mind, is this waveform AC or DC? What do you think? This is the 0 line right here. It's DC, because it doesn't cross, it never goes negative. So this is actually what we would call pulsating DC. It's only going in one direction, but it is pulsing up and down and up and down. So you look at that, and at first glance you'd say, that's an AC waveform. But actually, since it never goes the other way, we classify this as pulsating DC. And you'll see this in power supply circuits. So just heads up on that. I heard a comment tonight from, I think it was Craig, that said he doesn't like schematics very much, or it's hard for him to learn. That's okay, you'll get it. Schematics are the lifeblood of electronic technicians. It's what is necessary to trace out circuits and to find faults. And even now, your car is more electronic than it is mechanical anymore. And if you watch some of the repair videos on YouTube about electronic circuits in cars, there's a lot of schematics now that are provided for your automobile. And so here we have some simplified schematics. Here's our battery symbol again. Here we have a current being shown here flowing. Here is a resistor. We had a lamp at this point before, but now we have, this is the schematic symbol for a resistor. We don't know what value that resistor is. We don't know what value the battery voltage is. It's not provided on this schematic, but that's what we know. Over here we have an alternating current generator. That's the standard schematic symbol for that. We don't know what frequency or what amplitude that is, but okay. And again, we have a resistor with the load here. And you notice the current flows in one direction during part of the cycle and it flows back in the other direction. This is going on in your house, in your appliances, 24/7. So just keep that in mind. That's what I like about this class is it actually gives you some information you can use back in your own life, back at your house. You can look at that refrigerator and look at the wattage reading, and it's going to start to make sense. You go, oh, that's a 500 watt refrigerator, whereas this new one over here only uses 200 watts. We could save some money if we went to the new one, maybe. So, okay, right. DC generally is stored in batteries through chemical action. So here are lead acid cell batteries, for example, that you might find in your automobile or in other equipment. It stores energy in the batteries chemically. And there are new technology. Lithium iron phosphate is the latest that's got all sorts of different battery control modules built inside, but they're all storing energy chemically. All right, let me tell you a story. Coming back to me for a second, Bruce. You may know, I think I've mentioned, that I worked for the Voice of America. I was a field service engineer working primarily overseas at our overseas transmitting stations. And from 1990 to 1993, I was stationed at our transmitting station in Munich, Germany. Nice assignment, but I came from Liberia. That was my last assignment where I'd been evacuated, so it was kind of a make-up assignment. But anyway, it was good, and I was going to a meeting in downtown Munich, and in order to get there, I had to take a shortcut through the cemetery, the South Older Cemetery, Südalter Friedhof. Okay, and I'm trucking along trying to get to my meeting, and I'm rounding the corner, and I trip on a raised area of a grave. And I didn't fall or anything, but I look over at the gravestone, and what did I see? Laptop, please. It was the grave of George Simon Ohm, or as the Germans might say, Georg Simon Ohm, at the Südalter Friedhof. There's the gravestone. That's what I saw. I'd been involved in electronics for years and years and years. I had no idea that he was from Munich and that's where his grave was. So George Simon Ohm...
He was trying to inhibit you.
Apparently, he was resisting me somehow. But anyway, he is the one who is responsible for what we now know as Ohm's law. Now, last week you saw this. We talked about the pyramid with the relationship between frequency and wavelength. And the speed on the top there is the speed of light, 300 million meters per second. And then we had the frequency in megahertz and the wavelength in meters. And if we wanted to find the wavelength, we knew that we could divide 300 by the frequency in megahertz, and we'd get the proper wavelength in meters. Well, a similar relationship exists, and it's known as Ohm's law. And it has the three quantities that we talked about: the pressure, the voltage, E, the current, the amperage, I, and the resistance, ohms, and they form this pyramid, which I call the ear pyramid. Just remember it. E is on top, I on the bottom, along with R on the bottom. And similarly to the other pyramid, if we want to find the formula to determine resistance, let's say, if we put our big thumb over R, that leaves E over I, or E divided by I. Voltage divided by current, voltage in volts, current in amps, And if we do that math, we will determine the resistance in ohms. This pyramid gives us these three formulas. Resistance equals voltage divided by current. Current equals voltage divided by resistance. And voltage equals current times resistance. This is Ohm's law, developed by that German physicist that I tripped on in Munich. So it's the basis for, everyday calculations in the electronics workshop. You'll make measurements on things and go, okay, well, I know these things. Well, I want to find out something else. So we'll be using Ohm's law tonight in the test, but this is really, it's a very valuable thing to know. Along with Ohm's law, there's Watt's law. I believe it's named after James Watt, the American scientist. And this uses power in watts, current in amps, and pressure or electromotive force in volts. So that together we have two pyramids, ear pi, E over IR, and P over IE. If you can just put in your head ear pi, you can come up and you can derive these formulas. We can use them on some calculations. All right, if you're squeamish, don't look. But these two laws, Ohm's law and Watt's law, together, when you put them, give you all of these formulas. You don't need to know these formulas. I'm just saying that they're out there, and we'll talk more about them in the general class. But you can derive all of these formulas from ear pi, from Ohm's law and Watt's law. All right, back to circuits. So a series circuit is one where you have a power source. In this case, we've got a battery here. This is a pictorial, by the way. This isn't a schematic. This is a pictorial diagram. And the battery is connected to a switch. And the switch is then connected to one lamp, running through the lamp and out, to the next lamp, going through and out, to the next lamp, going through and out, and then back to the power source. One of the problems, Christmas is a great holiday, but when you're decorating the Christmas tree, and you got to get the lights out, and you plug it in. Oh, I hope it lights up. I hope it lights up, and it doesn't. You've got to go through and we must have a bad bulb, and so you're pulling one bulb out and putting a known good bulb in, and sometimes you get lucky and it lights up. In many cases, I've just gone and bought a new string of lights because that's a pain. But okay, that's a series circuit. The current that flows through one lamp flows through the next lamp, flows through the next lamp, flows through the and if any one of them opens up, none of them light up. So back to our pictorial here. So if this bulb goes bad, for example, this bulb and this bulb will not light either. So this is a series circuit. This is a pictorial diagram, a schematic diagram that is close to it there. Again, here's our schematic symbol for a battery, universally recognized. The lamps now are being replaced by resistors. So the up, down, up, down, up, down, that's a resistor. That's resistor 1, resistor 2, resistor 3, resistor 4. But in this case, it's a series circuit where the current is flowing through all of the resistors. And the current that is flowing through this resistor, the value is going to be exactly the same as the current flowing through this value. So if there's 1 amp of current that flows through this resistor, there'll be 1 amp of current that flows through this resistor, 1 amp of current that flows through this resistor, and so forth on this. So this is a series circuit. The opposite of a series circuit is known as a parallel circuit. So with a parallel circuit, in this case we have our energy source, a battery. But the lamps or the loads are connected across and back to the power source. Connected across and back to the power source. connected across and back to the power source. In this case, if one of these lamps burns out, the other two will continue to light. And what some of the Christmas tree manufacturers have done is tricky. They've put together series parallel combinations in some of their Christmas tree lights. So you'll get partial illumination on some of them. Anyway, this is a parallel circuit. And schematically, this is what it looks like. Here's our power source, the battery again, and the resistors here as the loads are connected directly back to the source. They go back to the source, back to the source. In this case, current that flows from the battery is being divided. So the current that flows through each of the resistors is only going to be a fraction of the total current that is being supplied by the battery. So that's when we talk about junctions. Here's a series junction, so we know that the current that flows through this resistor that's in series with this resistor, the currents are going to be the same. The current through R1 is going to be the same as the current through R2. Whereas with R3 and R4, the currents are going to be different. They're going to divide up. Part going through R3 and part of it going through R4. These are what we talk about current junctions in schematics. Now, conversely, if you have a source of power, they don't specify here, but I'm going to say it's 10 volts, and we have two resistors of equal value, then what happens is the current through them are going to be the same, and the voltage that drops across one and then across the other, because they're equal value, the voltage across this is going to be half of the source voltage, and the other half of the source voltage is going to be dropped across here. So you could use this as a voltage divider. So if you had 10 volts coming in, to let's say 10 volts DC, at this point you would measure there would be only 5 volts DC. And we use voltage dividers in circuits to give us lower voltages, or in audio circuits to give us attenuation. So voltage dividers are a very common part of electronics. Don't need to know the formula. You don't have to calculate that. That's in an upcoming class. And again, the voltage across parallel resistors is the same as the source. There's no division of the voltage here. If it's 12 volts coming in here, you will measure 12 volts on this resistor, or across this resistor, or across this resistor. We'll talk about measurement coming up here in just a second. So a common term that you've heard, but do you really understand what it means? Oh, I think I've got a short circuit. A short circuit is when something falls into the circuit board or whatever else and provides a path for the current that should be flowing through the lamp, but instead flows back to the power source. And so the lamp doesn't get any current. This is a short circuit. The wire that has fallen across there is shorted out the battery. This could actually generate a lot of smoke and fire. We'll talk more about that here in a second, but if it's a really high-powered device, for example. So that's a short circuit. The opposite of a short circuit is on the right here. This is an open circuit, where the wire has fallen off. Current can't flow because it's open here. It's like a switch that's open, so no current can flow. So this is an open circuit. We have the short circuit. A properly operating circuit could be called a closed circuit. And I mentioned that we could make a measurement of the voltage. We use meters. Meters display an amplitude on a numbered scale, and it could be an analog meter with a needle. This is what this is. Or it could be a digital meter, as we see here, with a digital readout. But these display amplitude on a numbered scale, and we can use them to make measurements in a circuit. And how do we connect for voltage, to measure voltage, or to measure current? So a voltmeter measuring pressure is connected across the device under test. So if we want to know what the voltage is at the lamp, we put the voltmeter in parallel with the lamp. If we want to know what the current flow is in that circuit through the lamp, for example, we have to break the circuit and put the ammeter in series with the load. I liken an ammeter to be, well, maybe they don't have them anymore, but at the old ball games, you had to go through a turnstile and it would go click, 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 and it would be counting the number of people. Well, an ammeter is kind of like that, only it's counting the number of electrons that are going through the circuit. So ammeter goes in series, a voltmeter goes in parallel. One of the first pieces of test equipment, and yeah, you'll probably want to buy one of these, is a multimeter. And get a good one, you know, don't cheap out, but you can get either analog types, although these are harder and harder to find, or a digital meter. This is a super cheap one. I wouldn't probably have you get one of these, but you can see they both have selector switches here, and you can switch them so that they can measure voltage, or they can measure current, or they can measure resistance. Those are the primary things that a multimeter will do. Now, some other fancier multimeters can do other functions, but those are the three basics: measuring voltage, measuring current, and measuring resistance. And some of the multimeters will measure AC and DC voltage, and some will measure AC and DC current. All right, now I'm going to let you in on a big secret. Come on back to me, Bruce. So, don't want to admit this, but okay. Electronics runs on smoke. Yeah, it does. Have you ever had a device go bad? You know, your TV's on the fritz and all of a sudden the smoke starts coming out? Think about it. Electronics runs on smoke. We don't want to let the smoke out. So no smoking. No smoking electronic devices. All right. That was a joke, but the reason is because that multimeter that I told you to buy, to invest your money in, can smoke. You can let the smoke out. It'll measure volts, it'll measure amps, it'll measure ohms. The problem is if you've got that little switch here set in the wrong position, if you have it, you think you're going to be measuring volts in a circuit that's active, but you have it inadvertently set on the resistance reading. When you do that, all of a sudden you'll see the smoke come out of the meter. You will damage the voltage divider resistors inside the meter. So this is a demonstration of electronics properly administered. It runs on smoke and you keep the smoke inside. We don't want to let the smoke out. And if you're going to be using a multimeter like I showed you there, but you're going to be measuring high voltages, think about it. The little probes that come with them probably is not adequate to measure anything like 1,000 volts or up. So you need a high voltage probe like this. And think about the meter that you buy. If you buy a cheap meter, it's going to come with, you know, inexpensive probes that are maybe not the safest. So good quality gives you safety. That's something that you're buying. And so whether it be an elaborate high voltage probe like this one is that can plug into your multimeter, or just the probes that come with a multimeter, you want something of good quality. All right. Here's a question that's on the test. Come back to me for a second, Bruce. That I don't know why they did it, but we're going to talk about it. And then we're going to talk about capacitors at length here in just a second. But let me talk to you about capacitors. Capacitors are really two metal plates that are brought very close together, and they're separated by an insulating material. It could be air, it could be plastic, it could be a special non-conductive coating, and what happens is if you put DC connected to one of the plates of the capacitor, electrons will build up on one plate and will leave the other plate up to a point when you've saturated the plate and all of the electrons are on there. And so then current will stop flowing through the capacitor. So we look at this circuit. This is a capacitor in a DC circuit. If the capacitor is of a certain value, for example, and we connect the battery up, electrons, we showed electrons flowing from the negative terminal, will flow through the bulb, flow through to the capacitor, start building up on this plate, adding additional electrons. It'll force electrons away from this plate and back to the battery up until the capacitor is saturated. It's charged and can accept no more electrons. The bulb in this case will light briefly and then go out. Likewise, you can use your ohm meter function on your multimeter to test capacitors by connecting up against to the capacitor, and they may be polarized, so you have to observe polarity. When you hook up your ohm meter to measure resistance, you'll initially get a very low resistance as the capacitor is charging, and then it rises to a high resistance. We'll talk more about this. This is, I don't like the way this has been positioned, but okay, we have to go with it. Oh, look, we're already at some questions for section 3.1. So if you're in the Zoom classroom, you can go ahead and unmute and tell me which you think is the correct answer. Remember, use the 3-second rule. Wait 3 seconds, if you would, before you make your answer, so it gives people a chance to think, and also if they're watching on YouTube. If you can, use the phonetic alphabet. This is a great time to practice. Alpha, Bravo, Charlie, Delta, A, B, C, or D. And these are the actual questions and actual answers that'll be on your test. Just remember that the answers will not be in the same order on the tests that you take. So don't memorize A, B, C, or D. That will do you no good. What we want you to know is the right answer. Okay. Electrical current is measured in which of the following units?
D is in delta.
D is in delta. Amperes, amps, that's current. Whereas Mr. Zielinski would say amperes. Electrical power is measured in which of the following units? Power.
B is in Bravo.
That's right, watts. What is the name for the flow of electrons in an electric circuit?
Delta current.
D, delta?
Yes, so the current is the electrons flowing through the circuit. And what are the units of electrical resistance?
C, ohms?
Yes, Charlie, ohms. And what is the electrical term for the force that causes electron flow?
Alpha voltage.
Voltage is the pressure, that's the force that causes the electrons to flow. Could be from a battery, could be from an AC generator. Why are metals generally good conductors of electricity?
B,
Bravo, yes, they have many free electrons in the outer ring of their atomic structure. So which of the following is a good electrical insulator?
B.
Bravo, glass. Yes, excellent. The others are good conductors. So which of the following describes alternating current?
C,
C.
Charlie?
Charlie, current that alternates between positive and negative. So which term describes the rate at which electrical energy is used?
C, power.
D,
Power, correct. And what type of current flow is opposed by resistance? Read carefully. You'll learn that's a trick of mine. Yeah, so what type of current flow could be opposed by resistance? Direct current? Yes. Alternating current? Yes. Radio frequency current? Yes. So the answer is all of those choices are correct. If you hear me say read carefully, that's a clue. So what is the formula used to calculate electrical power in a DC circuit?
B is in Bravo.
Alpha.
Oh, no, I'm sorry, Alpha. Yep.
Yeah, it is alpha. Remember the pi pyramid? So we're trying to find power, so we put our thumb over the P, and it's I next to E, or I times E, so power equals current times voltage, or I times E. How much power is delivered by a voltage of 13.8 volts and a current of 10 amps? So we're looking for power.
138.
D is delta.
Not D as in delta, no. I heard
As
it.
an alpha.
A is an alpha, yes. 13.8 times 10, E times I is 138 watts. How much power is delivered by a voltage of 12 volts DC and a current of 2.5 amps? Again, we're looking for power.
B.
Bravo, 30 watts. 12 times 2.5 is 30. 30 watts. So how much current is required to deliver 120 watts at a voltage of 12 volts DC? So now we're looking for current.
Yeah,
Bravo,
B.
10 amps.
Bravo.
Yeah, so it's 120 watts divided by 12. P divided by E is 10. 10 amps. So what formula is used to calculate current in a circuit? Now we're on to Ohm's law.
B is in Bravo.
E Bravo.
Yes, I equals E divided by R. And what formula is used to calculate voltage in a circuit? I heard A alpha.
A is in alpha.
Yes, A is in alpha. E equals I times R. Good. And what formula is used to calculate resistance in a circuit?
B is in Bravo.
Right. R is equal to E divided by I. All right, let's put it into effect here. What is the resistance of a circuit in which a current of 3 amps flows when connected to 90 volts?
E Bravo.
90 divided by 3 is 30. 30 ohms. Yeah, we were looking for resistance, right. All right, what is the resistance of a circuit for which the applied voltage is 12 volts and the current flow is 1.5 amps? So we're looking for resistance again.
C.
Yeah, I heard you. You were just kind of low in there. I was waiting to see if I heard somebody else. Yes, C. 12 divided by 1.5 gives us 8, or 8 ohms. And what is the resistance of a circuit that draws 4 amps from a 12-volt source?
A is in Alpha.
12 divided by 4 is 3 ohms. So what is the current in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms?
D delta.
Yes, 120 divided by 80 gives you 1.5. So what is the current through a 100 ohm resistor connected across 200 volts? We're looking for I.
C Charlie.
200 divided by 100 gives you 2. That is correct. And these are completely accurate Ohm's law calculations. So what is the current through a 24 ohm resistor connected across 240 volts?
C, Charlie.
Is in Charlie.
Yes, 10 amps. 240 divided by 24. What is the voltage across a 2 ohm resistor if a current of 0.5 amps flows through it? So we're looking for E.
A, 1 volt.
See that? E equals I times R. So I is 0.5 and R is 2. So 0.5 times 2 is 1. What is the voltage across a 10 ohm resistor if a current of 1 amp flows through it?
B, Bravo.
So we're looking for E, and E equals I times R. So Bravo is correct, 10 volts. And what is the voltage across a 10 ohm resistor if a current of 2 amps flows through it?
D, delta.
Again, we're looking for E, so E equals I times R. 10 times 2, 20. And in which type of circuit is DC current the same through all components?
Alpha series.
Series circuit. Yes, the current flows from one to the next, and they're all the same. And in which type of circuit is voltage the same across all components?
B is in Bravo,
That's
parallel.
the parallel circuit. And which instrument would you use to measure electric potential? Also known as force, also known as something else.
Bravo, voltmeter.
Voltage, voltmeter, yes. And how is a voltmeter connected to a component to measure the applied voltage?
B, parallel.
Bravo.
Yeah, voltmeters are connected in parallel with the device under test, yeah. So when configured to measure current, how is a multimeter connected to a component?
A in series.
Yeah, you have to break the circuit and put it in series with that. And which instrument is used to measure electric current?
D, delta.
Yep, an ammeter. You're measuring amps, so an ammeter is used to measure electric current. And which of the following can damage a multimeter?
C, Charlie.
Yeah, you'll let the smoke out if you attempt to measure voltage when using the resistance setting. Don't do that. And which of the following measurements are made using a multimeter?
C is in Charlie.
Voltage, resistance, and then current was the other one I mentioned. So yeah, voltage and resistance. So what reading indicates that an ohm meter is connected across a large discharged capacitor?
Increasing resistance with time, A.
It starts out really with a low resistance and then comes back up again because of the capacitor charging. So which of the following precautions should be taken when measuring in-circuit resistance with an ohm meter?
Is
it C,
Charlie?
Not C.
A is in
Not-
alpha.
No, not A.
You better be grounded.
B, Bravo.
Yeah,
it's
yeah.
B,
If you're going to
B.
make in-circuit resistance measurements, you don't want there to be power there because you'll let the smoke out. So ensure that the circuit is not powered. So which of the following precautions should be taken when measuring high voltages with a voltmeter?
Bravo.
Yeah,
B,
ensure
Bravo.
that the
B.
meter and the leads are rated for use at the voltages to be measured. And that, ladies and gentlemen, is the end of section 3.1. We're going to take our 5-minute intermission right now. So get up and stretch and move, and we'll come back and finish out the last 2 sections. we are back. A little comment to Brittany, who's watching us in the Zoom classroom. She had a comment asking if we could make the image any larger than it is right now. Unfortunately, no. I have spotlighted myself so that I should be larger than anyone else on your screen. You're probably going to have to get a device with a larger screen. Unfortunately, she has some vision problems, but you can always watch the YouTube video later again, maybe on a larger screen if there's something that you missed, and take a look at that. Also, I wanted to comment that yes, there was another comment from John that the classroom learning experience is better than reading the dry book. Yeah. And we focus in on the test questions that you will see. The book gives you a lot of great information that's in addition to the test questions, but sometimes it confuses you even more. So not to worry, we focus in on the test questions. And that's what we're going to do right now in section 3.2, which is about components and units. And you've already seen some of these already. Here's our friend, the resistor. This is the schematic symbol for a resistor, which is made out of a material specifically designed to resist the flow of electric current. And it could be carbon-based, could be a resistance wire, but resistors oppose current flow in a DC circuit. That's the definition that you'll see, although actually it opposes AC current and opposes RF, but DC circuit is what they want you to remember. And resistors, this is what they look like. They're measured in ohms. That's the unit of resistance. So resistors, they oppose the DC current flow, and voltage and current as they're flowing through a resistor are in phase. So if we had an AC current flowing through it, as the voltage peak goes up, the current peak goes up at exactly the same time. Well, Gary, wouldn't it always be that way? No. That's the magic of electronics. So we're going to be talking about that in a second. We're not going to go into it, but resistors are color-coded. And you can read the color code and tell you and know what the value of that resistor should be, plus or minus whatever their tolerance is, and that's indicated by the last band as well. So if you want to know more, you can follow the link here, and they'll tell you about the resistance color code, still used to this very day. Now, resistors, like you see above there, they're fixed two-terminal devices. Whereas you can also have variable resistors, which are typically three-terminal devices. And schematically, it may be something that looks like this, or this is more accurate, the three terminals, 1, 2, 3, corresponding to the 1, 2, 3 here on this variable resistor. Variable resistors are used for controls, for volume controls, for other controls and mechanisms. And the potentiometer, or variable resistor, it's measured in ohms, the total ohmic value from end to end here. This is a 1,000 or 1 kilo ohm resistor. This is a 10,000 or a 10 kilo ohm resistor. So the point from here to here, if you measured it with an ohm meter, would be, in this case, 10,000 ohms. So they're known as variable resistors or potentiometers. Our friend the capacitor. We talked about the capacitor with the two plates separated by an insulating material. You measure capacitance in a unit called the farad. And most capacitor values are much smaller than 1 farad. So we talk about millifarads, microfarads, nanofarads, and picofarads. And so here are some schematic symbols for capacitors. Here's a fixed capacitor, kind of looks like the two plates that we talked about. Here is a polarized, probably electrolytic capacitor. This capacitor has to be put in the circuit in one orientation only. And the circuit board will probably have it noted, which is the plus end. If you put electrolytic capacitors in backwards in a power circuit, they can blow up. You don't want that. You'll let the smoke out. Don't do that. But that's what this is all about. And here is a variable capacitor. We'll look at one of these here coming up in a second. So capacitors look in all different shapes and sizes. Back in the day when I was first studying electronics in the 1970s, it was physically impossible to build a 1 farad capacitor. We got the millifarads, the microfarads, the nanofarads, the picofarads. Those were possible, but to build a 1 farad capacitor, there wasn't enough room. Well, look now. You can go to Mauser Electronics and you can buy one of these. This is a 3,000 farad capacitor at 2.7 volts. It's more like or more akin to a battery than it really is to a capacitor. But how times have changed. Now you can buy a 1 farad and greater capacitor. And these capacitors are known now as supercapacitors. They actually have enabled some circuits to be developed that could not be developed before. I mentioned the variable capacitor. Here's one that was common in radios back in the day, the superheterodyne tube radios. It has a stationary section known as the stator and a rotating section known as the rotor. And as these meshed together, more plates would come across from each other, the capacitance would go up. And as you separated them, the capacitance would go down. And this is how you would tune the frequency on an AM radio back in the day using a variable capacitor, much like this. So no matter whether it's a fixed or a variable capacitor, capacitors block DC current flow, except for that brief, we talked about it there, inrush of electrons. So capacitors will block direct current flow after that inrush. Capacitors resist AC current flow. It'll pass it, but it kind of resists it. It stores energy in an electric or electrostatic field. If you're putting AC current through a capacitor, the electrons are building up on one plate, then their polarity reverses, and then the electrons build up on the other plate, and back and forth and back and forth. And this back and forth creates an electrostatic, also known as an electric field. The ability to resist AC current is called capacitive reactance, and it's written as X sub C. And capacitive reactance is measured in ohms. So we call it ohms. It's not exactly the same as the resistive ohms, but we use the ohms to tell us about capacitive reactance. And so we looked at it. Here's an AC generator. And current will at first, so let's say, flow in this direction. It'll build the electrons up on this plate, and then current reverses, and electrons will start to build up on this plate, back and forth, creating an electric field where energy is stored. So capacitive reactance, it opposes AC current, and the voltage and current at the capacitor are out of phase due to the creation of the electric field. So we say that with capacitors, current leads the voltage. Current goes into the capacitor before the voltage charges up, and then alternates polarity and goes the other way. Current leads voltage in a capacitor. Much more information about this in the general and the extra class. All right, inductors. This is an inductor. It just looks like a coil of wire. Well, that's what an inductor is. In this case, it's a coil of insulated wire held very closely together. And inductors can be used with air cores, or you can wind them on ceramic materials, ferrite materials. They can be inline, or they can be on toroids, the donut shaped there. And inductors in a schematic look like this. So here we have, it looks like a coil of wire. This is an inductor. This is not a resistor. This is not a capacitor. This is an inductor. L1, L2, L3. So we have 3 inductors in this circuit. Is this circuit a series circuit or a parallel circuit? What do you think?
Parallel circuit?
Yeah, it's a parallel circuit. I got the number 2 being held up. That's great. All right. Inductance, we said that the unit of capacitance was the farad. The unit of inductance is the Henry, named after this gentleman. And it was, back in the day, you could build a 1 Henry inductor. That wasn't no problem. Then they also built smaller ones, millihenries, etc. But inductance, measured in henries. Inductors, because they're a wire, they will pass DC current. So that's different than a capacitor. Inductors will resist AC current flow, but they store energy in a magnetic field. Remember, capacitors store energy in an electric field. Inductors store energy in a magnetic field and resist the AC current flow through a property called inductive reactance, or X sub L. And that reactance, its opposition to AC current flow, is measured in ohms. Again, not the same as resistance ohms, but we use the ohms symbol. All right. Inductive reactance opposes AC current flow, and again, in this inductor, voltage and current at the inductor are out of phase with each other due to the creation of that magnetic field. In an inductor, we say the voltage leads the current. The voltage comes up before the current starts to flow. More information than you need to know, but I'm trying to build a foundation for the upcoming classes. So a special kind of an inductor is one that uses a shared core. So in this case, we have a laminated iron core, and so we have our first inductor, which is what we call the primary of a transformer, the primary winding of a transformer. And on that same core, we have another inductor wrapped, wound. And this becomes the secondary winding of a transformer. And in this case, if we look at the number of windings here versus the number of windings here, this is what we would call a step-down transformer. If 120 volts was coming in here, 24 volts, let's say, might come out over here. And so transformers are in common use in all sorts of electronic and electrical devices. And in a schematic diagram, this is what it looks like. So here's our plug to go in the wall. We have a switch, a fuse, which is used for overcurrent protection. Here's the schematic symbol for a fuse. Here's our transformer. And notice the number of windings over here and the number of windings over here. This represents the iron core. So this, again, is a schematic diagram for a step-down transformer. Impedance. I'm going to send you a short story to talk about impedance. Impedance is the opposition to AC current flow caused by the combination of resistance and reactance, either inductive or capacitive reactance. So when you put the two together, resistance in a certain amount and reactance in a certain amount, then you get the combination of those two is impedance in this magnitude. So impedance is a unit of measure to opposition to AC current flow, and again, we use the ohm. Okay, I know it's confusing. There's going to be a slide coming up just to review this, but yeah, for all of these, we use ohms. Don't ask me why. All right, so switch types, we looked at the very simple single pole, single throw switch. That's here, that we saw that in the circuits. Here's something called a single pole double throw switch, where you can take this current coming in, either have it go this way or have it go this way, a single pole double throw. And of course, then there's double pole single throw and double pole double throw. Just want you to know about these various switch types that you might see in circuit diagrams, and these are the schematic symbols for those. Well, the one I really want you to know about is single pole double throw. And These are mechanical switches. You actually have to walk up to them and flip the switch. You may have an electronically controlled switch, a relay. It may be controlling power at one location, but you're controlling it from another. And so a relay is an electronically controlled switch. This is what they look like in real life. So just be aware that they exist and are used in a lot of ham radio equipment as well. I mentioned a fuse as a protective device, also circuit breakers. They'll open the circuit if too much current is drawn. And you always want to use the proper size. If you're replacing a 5 amp fuse is blown, don't put a 20 amp fuse there. You'll let the smoke out. Now put a 5 amp fuse, see if it blows. If it does, then you know you got a problem in the circuit. But always use the proper size. This is just the briefest skim on electronics information. We cover so much information. Semiconductors could easily be a semester-long class at community college, and there have been advances in semiconductors, but we're going to cover it here in just a few minutes. But the most basic of semiconductors is the diode, and a diode allows current flow in only one direction, and it has an input for current flow called the anode, and an output for current flow called the cathode. Notice the arrow shape here. That's current will flow from positive to negative this way. And this is what it looks like in real life. The stripe you see here indicates the cathode. Anode and cathode are old vacuum tube terms, but they carried over. And so this is a silicon diode. And when you put current flow through it, you're going to have a voltage drop across this diode of about 0.6 to 0.7 volts DC. That's normal. That indicates a normal working of a silicon diode. Now there are also germanium diodes. They were actually the first ones. This one right here, it was used and still is used for detectors for AM radios to actually get the signal transformed from radio frequency to audio frequency. It involves one of these. Now I mentioned that the silicon diode has a 0.7 volt voltage drop across it. The germanium diodes only have a 0.2 volt forward bias or voltage drop across them when they're operating. Notice the stripes. That indicates the cathode. So here's the anode end and here's the cathode end. Germanium versus silicon. Now silicon diodes are used in power circuits. You wouldn't find a germanium diode there. But so here is a 120 volts AC coming to a bridge of 4 diodes, creating pulsating DC. Remember that waveform we looked at earlier? Going up and up and up. That's pulsating DC. That's what you would see right here. And if you then send it directly to a load, well, it'll heat up the load just fine. But normally in a power supply, you go farther than that. You actually have the rectifier circuit. You have the pulsating DC, like we saw here. Then we have filter capacitors. And the filter capacitors smooth out this pulsation, so there's just the smallest of ripple is what we call it up there. So this is mostly DC, and then after that there's usually a voltage regulator stage that will hold it at a constant voltage. So a lot of ham radio equipment is 12 volts, or actually the standard is 13.8 volts. And so if you're going to buy a transceiver for your new ham shack, for example, you'll have to buy the transceiver and likely have to buy a power supply to power it. And this is what the power supply is going to look like. It'll have your AC input, you'll have a transformer, you'll have a rectifier, you'll have filter capacitors, and then you'll have a voltage regulator, and then here's your transceiver being the load using pure DC. This is a block diagram of a regulated power supply. Diodes, I didn't know this until I started doing the class. All diodes emit light when they're conducting, except most diodes are enclosed and so you don't see it. But a Russian actually invented the light-emitting diode. Light-emitting diodes are designed to purposely emit light, and they've replaced lamps as indicators for most equipment. So here we have, for example, a DC power source, a battery, a current limiting resistor, and then the LED. And so this is the basic circuit for all LEDs. You can't omit this resistor. If you connected the LED directly to the power source, it'll flash and be done. You have to have that current limiting resistor. But forward voltage through the diode, making it to conduct, causes photons to be emitted. And so we no longer have indicator bulbs, the incandescent bulbs, rather LEDs have taken over. So diodes are the most basic of semiconductor devices we use right now. Transistors came along next. The name is derived from transfer resistor, and it's where an input voltage or current coming to a transistor can be used to control the output voltage or current. And what happens is that with one circuit, you can have a small signal at the input. It's amplified to a larger signal at the output, so you can use the transistor as an amplifier. That's one use. Or the transistor can have a small signal at the input, which can turn it totally on or off. That's using the transistor as a switch. And the first transistors were bipolar transistors, made up of 3 layers of semiconductor material that were specially treated to either have an excess of electrons or an absence of electrons. We won't go into depth, but there's P-type material with an absence of electrons and N-type material with an abundance of electrons, and putting them together in PNP or NPN configuration gives you a transistor. And so this is the schematic diagram for a bipolar transistor. Note that the arrow is pointing toward the center here. The arrow points toward the negative, so this would be a PNP material. Here it's pointing away, so this would be an NPN transistor. These are bipolar transistors. They're 3-legged devices. They have a base lead, they have an emitter lead, and they have a collector lead. Base, emitter, and collector. And you have to actually maybe take a look at service literature to find out which is which on a 3-terminal device. But here are some examples of transistors. This is a power transistor. It's capable of handling higher power levels. And in a schematic diagram, here's our bipolar transistor, a base, emitter, collector. All right, what are these devices? What do you think?
Resistors.
Those are resistors. What do you think this is?
Capacitor.
That's a capacitor, and it's a polarized capacitor. It has to go in one way, all right? And what is this again?
It's another polarized capacitor.
Correct. This right up here?
That's a
9-volt battery.
That's a battery, exactly. So this transistor is being used as an amplifier. We have a very small input signal, 0.025 volts peak to peak. It goes through this amplifier and it comes out as 2.5 volts peak to peak. So it is amplifying the waveform. That's number one. Also notice something, that the input goes positive and then negative, whereas the output goes negative and then goes positive. This is also known as an inverting amplifier. It is actually changing the phase of the signal. This could be an audio signal in your radio, for example, a stage of gain inside the radio. This is, but common emitter configurations, which is what this is, do this. They'll invert the phase of the signal. That's a bipolar transistor. The next type of transistor was the field effect transistor. And instead of the base, emitter, and collector, they have a gate, source, and drain. And again, the arrow points toward the N-type materials. This is known as an N-channel FET. Here is a P-channel field effect transistor. And they're built kind of like this, and there's different ways that they can be configured, but current can flow from the source to the drain unless it's inhibited by the gate or unless it's enhanced by the gate, depending on the style of FET that you have. And in a schematic diagram, this is what an FET looks like. These are bipolar transistors on the left and right, but this is a field effect transistor, a P-channel field effect transistor. Integrated circuits combine a lot of this material all in one chip. So you may have multiple transistors, multiple other devices. Large-scale integration puts just thousands, if not millions, of devices into one integrated circuit. All right, that's all we need to talk about there. All right, radio magic. That's the next circuit I want to talk about. Resonant circuits. Remember I told you that the voltage and the current through a capacitor are not in phase, and the voltage and current in an inductor are not in phase? That's because some of the energy is being stored in either an electric field for the capacitor or a magnetic field for the inductor. Well, when you put them together in either series configuration or parallel configuration, you get what is known as a resonant circuit. And in a series resonant circuit, at a certain frequency, at only one frequency, the resonant frequency, the inductive reactance and the capacitive reactance cancel. And it actually becomes almost a short circuit at that one frequency. Whereas in a parallel resonant circuit, it becomes an open circuit at that frequency. In a parallel resonant circuit, here's a animated GIF that shows you the energy is transferred back and forth very fast between the inductor and the capacitor. And at the resonant frequency, they almost kind of disappear. So that's the beauty of a resonant circuit. And why is that important? Well, this is the whole basis for tuning and for impedance matching the devices that we use at resonance. And remember, I talked to you about then impedance. The impedance is the combination of resistance and reactance and the magnitude of that. So just be aware that it exists. Oh yeah, the ohms, resistance, that's measured in ohms. Capacitive reactance, that's measured in ohms. Inductive reactance is measured in ohms, and impedance is measured in ohms, but you can't just add them together. You have to know what you're doing when you're using them. And the definitions, resistance of the opposition to DC current flow, that's resistance. Impedance is the opposition to AC current flow by definition for the test. Okay, let's do some questions. So what describes the ability to store energy in an electric field?
Delta.
E is in delta.
Yeah, capacitance uses the electric field to store energy. And what is the unit of capacitance?
Alpha.
Couldn't build them before, but yes, the farad. And what describes the ability to store energy in a magnetic field?
Delta.
Inductance, indeed. And what is the unit of inductance?
C.
Charlie.
Yep, the Henry, named after Joseph Henry. And what is the unit of impedance?
Delta.
Delta.
It's one of those ohms, okay. And what is impedance? By definition.
A.
The opposition to AC current flow. And what electrical component opposes the flow of current in a DC circuit?
B.
Bravo.
Yeah, that would be a resistor or resistance. And what type of component is often used as an adjustable volume control?
Charlie.
Yep, the potentiometer, also known as a variable resistor. And what electrical parameter is controlled by a potentiometer?
B.
Yep, resistance, it's a variable resistor, yeah. And what electrical component stores energy in an electric field?
Bravo.
Yep, capacitor. They double up on some of these questions, but that's okay. What type of electrical component consists of conductive surfaces separated by an insulator?
Capacitor.
That too is a capacitor, D. And what type of electrical component stores energy in a magnetic field?
Charlie, C.
That's an inductor still. Yep. See, they doubled up again on this one. So what electrical component is typically constructed as a coil of wire?
Delta.
Indeed, the inductor. And what is the function of a single pole double throw switch?
Alpha.
Alpha.
Not alpha. Single pole double throw.
Oh.
Charlie.
Charlie, a single circuit is switched
Yeah.
between one of two other circuits. And what electrical component is used to protect other circuit components from current overloads?
A.
Alpha.
That would be the fuse.
Alpha.
All right, here's one that Craig doesn't like. Here's a pictorial, or a schematic, I should say. What type of switch is represented by component 3?
A. Alpha.
That is a single pole, single throw switch. Very good. And which is true about forward voltage drop in a diode?
Bravo.
No? Think about my germanium and my silicon diodes.
Alpha.
It is lower in germanium than it is in silicon, so it's lower in some diode types than others. It's a way you can identify what kind of diode you have as well, too. So what electronic component allows current to flow in only one direction?
Charlie.
Yep, that's the diode. And which of these components can be used as an electronic switch?
Charlie.
That's the transistor. That's one of the two functions it can do. So which of the following components can consist of 3 regions of semiconductor material?
Triode.
No. A triode is a vacuum tube. Semiconductor
Bravo.
material. That's a transistor. It's got an N-type, P-type, and N-type. So that's what they're talking about here, the bipolar transistor. And what type of transistor has a gate, drain, and source?
Bravo.
The field effect transistor has a gate, drain, and source, the 3 leads. And how is the cathode lead of a semiconductor diode often marked on the package?
E. Bravo.
Yes, with a stripe. And what causes a light-emitting diode to emit light? A alpha, when it's hooked up so that it conducts with a current limiting resistor, you have forward current flowing through it, then it will emit diode. If you reverse the polarity, the light will go out. So what does the abbreviation FET stand for?
D. Delta.
Yep, field effect transistor. And what are the names for the electrodes of a diode?
Charlie.
Charlie.
The
Charlie.
anode and the cathode. And which of the following can provide power gain?
A.
Alpha.
No. B bravo, the transistor. The transistor can provide gain. A transformer can transform the voltage, but it can't provide power gain. So, yep, transistor. So what is the term that describes a device's ability to amplify a signal?
Alpha.
A alpha, the gain, indeed. And what are the names of the electrodes of a bipolar junction transistor? What are the three leads?
Bravo.
The emitter, the base, and the collector. And what is the name of an electrical wiring diagram that uses standard component symbols?
Charlie.
Yes, Charlie, that's a schematic diagram. Oh, here's one. What is component number 1?
Transistor.
Alpha.
Alpha.
Alpha, that's a resistor. And what is component number 2?
That's B. B is in Bravo.
Yeah, it's a transistor. And what is component number 3?
C, Charlie?
Yeah, this would be a
C,
lamp.
lamp, yeah.
Yep. All right, what is component number 4?
Delta.
That's a battery. All right, and this schematic, what is component 6?
Bravo.
It's a capacitor, bravo, yes indeed. And what is component 8?
D. Delta.
It is. It's a light emitting diode. That's what this is indicating here, that light is coming off of the diode, so it's a LED. And what is component 9?
Charlie.
Yes, it's a variable resistor. And component 4?
Delta.
That's a transformer. And in this diagram, what is component 3?
Delta.
Delta.
It's an inductor, because it's got a tap that you can move up and down, it's a variable inductor. Good job. And what is component number 4?
A.
Yep, it's an antenna. We didn't talk about it, but yeah, that's the schematic symbol for an antenna. So which of the following is accurately represented in electrical schematics?
C, Charlie.
C, Charlie, component connections. And whoever gave that answer, your audio's down a little bit, but I can hear you. So which of the following devices or circuits changes an alternating current into a varying direct current?
Bravo.
B, Bravo.
That's where we saw the 4 diodes connected as a rectifier, or bridge rectifier. All right, and what is a relay?
Alpha.
It is an electrically controlled switch. And which of the following displays an electrical quantity as a numerical value or numeric value?
C,
Yep, that's a meter. Could be analog or it could be digital. And what component changes 120 volts AC power to a lower AC voltage for other uses?
Bravo.
That's a transformer. The step-down transformer that we saw. And which of the following is commonly used as a visual indicator?
Alpha.
A.
Yeah, you can look at your TV set right now probably and see an LED on. All right, which of the following is combined with an inductor to make a resonant circuit? So a resonant circuit has an inductor and a
D. Delta.
capacitor, correct. An inductor and capacitor together make up a resonant circuit. And what is the name of a device that combines several semiconductors and other components into one package?
C,
Charlie.
Charlie.
That's an integrated circuit. Yeah, pretty basic. So what is the function of component 2?
Charlie. Or no,
A, alpha.
No. You had it right. It's to control the
Charlie.
flow of the circuit. It's a transistor being used as a switch. Transistors will not give off light. That would be the lamp's job up there. All right. Which of the following is a resonant or tuned circuit?
alpha.
Yes, it's an inductor and a capacitor. You have to have those in either series or parallel. And what is the purpose of a fuse in an electrical circuit?
D, delta.
Bravo.
Bravo. It's to remove power in the case of overload. It doesn't limit current in any way other than to turn it off, and it doesn't prevent power supply ripple. So it just removes power in case of an overload.
Okay.
So why should a 5 amp fuse never be replaced with a 20 amp fuse?
Cause smoke.
Yes. It could cause smoke. Excessive current could cause a fire and let the smoke out. Yeah, you don't want that. All right. Last section for tonight, radio circuits. So you've probably all been to an auditorium, a basketball game or something like that where they have a PA system. I remember high school basketball was notorious for this. And somebody would turn the gain up on the public address amplifier up too much, and you'd get a howling or a ringing in the basketball court there. That's feedback. And feedback can be used in electronic circuits to generate an AC or an alternating current signal. And when you do that on a controlled basis, you have an oscillator. An oscillator creates an AC output signal. So you have an amplifier with gain that has output, and then you take some of that output and feed it back to the input selectively, and this will continue to then generate an AC output that you can tap off here and send to another circuit. So an oscillator generates a signal, a radio frequency oscillator, on just one frequency. In this circuit we have the transistor being used for gain, and we have a crystal over here being used as the filtering mechanism to determine what frequency this oscillator will operate on. Now after this we might follow it up with a filter. Filters are used to reject unwanted signals. There are various types. There's high pass, which means that it'll pass frequencies above a certain frequency, but block those below that. Or you can have low pass, where only the lowest frequencies get through, or a band pass, where you limit the frequency range which can get through, or you can have even notch filters that cut out just one frequency. Maybe it's an interference frequency. All of these are probably on a radio receiver or transceiver that you will have. You can adjust all of these things. And wide and narrow bandwidth, the bandwidth of the bandpass or notch filters. So you can have discrete filters, and you can have digitally created filters in digital signal processing, both. And so here's a simple analog circuit for a low pass filter, a resistor in the signal path with a capacitor going to ground. As the frequency goes up, more signal will be shunted to ground because of capacitors, the way they work. So this is a low pass filter. And a high pass filter has a capacitor in series and the resistor going to ground. So just the reverse. And this is the spectral display, or the spectrum of passing low frequency signals but blocking higher frequency signals. And this one blocks low frequency signals but passes high frequency signals. Those are filters, just an introduction. Now a transmitter can be as basic as this. Here's a Morse code transmitter with an oscillator generating that AC signal in a radio frequency, a driver amplifier, and then a power amplifier to go out to the antenna, and a Morse code key that could be controlling the driver or controlling the power amplifier or both. This is a block diagram of a simple Morse code transmitter. And when we turn on and off in a systematic way using Morse code symbols, dots and dashes, we are modulating the radio frequency carrier. We're adding information to that radio frequency carrier. Now, simple as on and off with a Morse code key. You can also modulate a carrier with audio signals. So this is the audio signal up here on the top. Here's our radio frequency carrier at a much higher frequency, and you can see that the amplitude, once it's modulated, the amplitude of the radio frequency carrier varies in step with the modulation up here. So this is known as amplitude modulation, or AM. Down below, we have the radio frequency carrier's frequency being changed in step with the modulation up above. This is known as frequency modulation. So the adding of information to a radio frequency carrier is called modulation. And a block diagram of an AM transmitter would look something like this with, again, here's our oscillator generating an AC frequency, an amplifier, a power amplifier here, and the power amplifier is actually driven by an audio amplifier that changes the amount of power that goes to the output amplifier. And when you do that, and you use the audio amplifier to amplify a microphone, you generate an AM signal. So this is actually the block diagram of an AM broadcast transmitter in its simplest form. So that's on the transmit side. On the receive side, we have receivers. This used to be a popular one back in the 1970s, kind of obsolete now, but they used superheterodyne techniques. It was the most common radio in the past, and what happened is you had an antenna that was connected up maybe to an amplifier or maybe directly to the mixer stage, and the mixer stage had connected to it an oscillator, a radio frequency oscillator, and the job of a mixer is to convert signal frequencies. So you might have a signal coming in on 1.6 megahertz. It would mix in the mixer with this signal here and come out at 455 kilohertz to an intermediate frequency amplifier, and then to, in this case, a product detector. Product detectors are used for single sideband and Morse code, and then an audio amplifier. But a mixer's job is to change one frequency to another, and it does it kind of mathematically. When you have two signals coming into the mixer, you will get out four signals. You'll get out the original signal, you'll get out the oscillator signal, you'll get out their additive product, and you'll get out their subtractive product. And so four signals are the solution for mixer math. But the whole purpose of a mixer, you have filters on the output of it, so you only get the frequency that you want out. And is to convert from the original frequency where it was coming in into an intermediate frequency, or converting from one frequency to another. And then after you've done that conversion, then you've got to get the modulation out of the radio signal, and you do that through a demodulator. So it could be as simple as that small germanium diode that you saw earlier. That would be an AM detector or AM demodulator. It could be the product detector that we just saw there, which is used for single sideband and Morse code. Or it could be an FM discriminator, which is used for demodulating FM signals. So just some background on some radio circuits that you should probably know about. All right, last set of questions. Which of the following is used to convert a signal from one frequency to another?
Bravo.
That's the mixer. And what is the name of a circuit that generates a signal at a specific frequency?
Delta.
That's an oscillator with a feedback circuit. And which of the following describes combining speech with an RF carrier?
Charlie.
Modulation, indeed. And that, ladies and gentlemen, is the end of Chapter 3. We made it. Let me see if I can find my cursor here, and I will remove the spotlight in the Zoom classroom. Does anyone have any final comments or questions that we'd like to talk about before we go tonight?
Question,
Yeah.
Gary, we didn't talk about a field effect transistor too much. Why would you use that instead of a bipolar? Like, how do you differentiate?
Okay, this is not required for the test, but just to let you know, bipolar transistors, which were the first ones, they're what we call current devices. They require a current to turn it on and off. Field effect transistors are more voltage devices that are more sensitive to the voltages that come in. What this boils down to is that field effect transistors are used a lot in RF circuits and radios at the front end, where low level signals are coming in and you need an amplifier that's likely to be a field effect transistor amplifier at that point. They have different characteristics, and the designers will try to choose the transistor type and for the application. You can have power FETs. There are all sorts of different things that are available now that didn't used to be available. But bipolar and FETs, they're not interchangeable. You can't replace one with the other, but they have different values that designers like to use for certain applications.
Great, thank you.
You bet. Any other questions or comments? Oh, your brain is smoking. Don't let the smoke out. Go take a break, get something to drink, have a great evening tonight, and we'll come back next week with Chapter 4. Until then, let me say, 73. See you next week.
Thank you.